Great to introduce the last speaker of this workshop, Urs Frauenfelder from Augsburg, and he will tell us about abstract Floer theory.
Thank you very much. And since I'm the last speaker, I think we should first give a big hand to these organizers, which did a wonderful job. Yes, so I would like to talk about abstract Flur homology. And this is joint work with Joa Weber, joint Joa Weber. And maybe let me first try to give you some motivation why we want to do this. So motivation for studying abstract Flur homology is kind of understanding Hamiltonian delay equations. And maybe let me also give you some motivation for the motivation. So why are we interested in Hamiltonian delay equation? And I would like to, as a motivation, to tell you first a bit about a gateway to the moon, to motivate why we would also like to have some kind of more general Hamiltonian systems. So motivation. For motivation. So gateway. So what is a gateway to the moon? So gateway to the moon is a periodic orbit around the moon. And now, strictly speaking, such a gateway does not exist. So that's maybe not so good for motivation. So the moon is not really periodic. And so actually, an actual periodic orbit we can never find. But we have better and better approximations to the truth around the moon. And if we make this our approximation better and better, at the end we also get to Hamiltonian delay equation. And let me explain you a bit how this goes. So we have here different levels of accuracy. And so level 0 is you just consider gateway and moon. Also that's level 0, just gateway and moon. So if you just consider gateway and moon, that's, yeah, so we have here our moon, and then we have around the moon our gateway. And that's just a Kepler problem, and we know to solve this. That's a Kepler problem. But around the moon, so the Earth is quite heavy, and therefore around the moon we should also take into account the gravitational action of the Earth. So that's a bit more sophisticated level. So we have gateway, moon, and Earth. And then if we consider these two, then we are back what Pedro explained us yesterday. This we can model as a restricted three-body problem. That's a restricted three-body problem. And so in the restricted three-body problem, as we learned yesterday from Pedro, so usually we are studying this in rotating coordinates. So we have the Earth is fixed, and we have also a fixed moon, and then we have our little gateway here, which is moving around the moon. So we have rotating coordinates. Earth and moon at rest. And the advantage is, if we study this problem in rotating coordinates, we have preserved energy. We have seen yesterday, Pedro has written down the Hamiltonian. So we have preserved energy. Now, usually you don't find just a gateway, a periodic orbit by chance. So, but if one studies this periodic orbit problem, one usually looks at the global point of view and looks at families of periodic orbits. And now, if you have so the gateway should not collide with the moon. That would be a bit bad for the gateway. But if you look at the global picture, then in the family there might be periodic orbits which collide with the moon. And yeah, so we have families of periodic orbits. And there, in such families, usually we also will see collisions. But as we have learned yesterday in talk by Pedro, we can always regularize these two-body collisions. Regularization of collisions. And there are actually different methods. One is Moser regularization, another is Levi-Civita regularization. Yesterday we have seen another one, this elliptic elliptic hyperbolic coordinates. But what is kind of for all these regularization techniques, what you do is we blow up the energy hypersurface. So we blow up the energy hypersurface that we get an additional part where the collisions occur. So this is a blow up of energy hypersurface. Good. So that's level 1, and now there comes level 2, and level 2 is so close to the moon. We have not just the gravitational attraction of the Earth, but as well the gravitational attraction of the Sun. So we have actually get a four-body problem. So we have a gateway, moon, Earth, and Sun. And now, if we also bring into account the Sun, then what we can still do, we can choose the coordinates so that Earth and Moon are at rest, but then our Sun will not be at rest. So the Sun is moving. So what we can do is we have here Earth, and here we have Moon, and then we have our gateway. And yeah, of course the Sun is a bit far away, maybe here, but the Sun is also moving. So there are no coordinates. Where all three of them, Earth, Sun and Moon are at rest. So in this, if we study this problem, then what we get is a Hamiltonian which depends on time. It will depend periodically on time, so that the Sun will move periodically, but also we have a time-dependent Hamiltonian. And so as soon as our Hamiltonian depends on time, we don't have preserved energy anymore. So the drawback is no preserved energy. But so this blowing up energy hypersurface does not make so much sense because there is no energy hypersurface. But luckily, recently there was discovered a new regularization technique, and this goes back to Barutello, Ortega, and Versini. And this new regularization technique is one doesn't blow up energy hypersurface, but one does blow up the loop space. So we have a new regularization technique. Discovered by Barutello, Ortega, and Versini. And so you blow up loop space. So, and this blow up is a non-local blow up, namely you reparameterize each loop, and the reparameterization depends on the loop. So this is non-local. So each loop is reparameterized, and a reparameterization depends on whole loop. And therefore, because this depends on the whole loop, the regularized problem you get will not be an ODE anymore, but it will be a Hamiltonian delay equation. It depends on the whole loop. So we get Hamiltonian delay equation. Yeah, so that's kind of motivation why we are interested in studying Flur homology for more general Hamiltonians. Other motivations could come from semi-classics and so, but I would like now to stop with motivations. And now but what is so special in Flur homology? So in Flur homology, so roughly speaking, we can say Flur homology is kind of a semi-infinite dimensional Morse homology. So, Morse index and co-index, they are both infinite, but so stable and unstable manifold would be infinite, but somehow their intersection is still finite dimensional, and this intersection, so one looks at the linearization of gradient flow lines, and this linearization of gradient flow lines, they give a finite dimension. They are Fredholm operators, and so this dimension somehow corresponds to the intersection of stable and unstable manifolds, which are both infinite dimensional. So we have infinite dimensional, stable and unstable manifold, but we have a finite dimensional intersection. And this so if we have a gradient flow line, then we look at the linearization of a gradient flow equation, and we get Fredholm operator. And another thing which is very peculiar in Flur homology, so in the Hessian at critical points, this is an isomorphism, but it's not an isomorphism from one Hilbert space in a fixed Hilbert space, but it's an isomorphism in a scale of Hilbert spaces. So Hessian at critical points is isomorphism for scale of Hilbert spaces. And so what is such a scale? So scale of Hilbert spaces. So we have actually two Hilbert spaces. So we have two infinite dimensional Hilbert spaces together with an embedding of one into the other, and this embedding is dense and compact embedding. So example, in case of the loop space, we could take H2 is W2 two loops, Rn, and H1 is W1 two loops, S1 to Rn. And because we have these two levels, so actually the space where we were working on is not the space in usual sense, but it's kind of a two-level manifolds. So we get a two-level manifold. Okay, now so when I say linearization of gradient flow equation, let me briefly recall to you what actually is the somehow linearization of gradient flow equation, and I would like to give the global picture to recall this just in the case of finite dimensional Morse homology. So linearization of gradient flow equation so we recall the finite dimensional case. So we assume M is just a finite dimensional manifold, and I would like to assume that my manifold is just C2 manifold. So this C2 is in traditional Flur homology, and so it is this number of derivatives is usually not a big problem to have infinitely many. But as soon as you get to delay equation, third derivatives get a disaster. And so that we have two derivatives makes somehow sense in if you think of Morse homology. Definitely we need a first derivative because we need a gradient, but then we also need a Hessian. So we should have two derivatives. And so let's assume that our manifold is this a C2 manifold, finite dimensional. And F from M to R is some C2 Morse function. And we have x minus, x plus, two critical points of F. And now then one looks at H, and this is the Hilbert manifold of W12 path from x minus to x plus. Right, so they are not necessarily solutions of the gradient flow equation, that they are just W12 paths, and this Hilbert. So if I assume that my manifold M is C2, then this Hilbert manifold of path, this will be a C1 Hilbert manifold of path. And so the tangent space, if you have such an X in this space, so the tangent space, this is just, these are W2 vector fields along X. Along X. And so this tangent space, as a tangent bundle, the tangent bundle would be then just C0. But we have another bundle, kind of the weak tangent bundle, namely this L2 bundle. So we have L2 bundle. Let's call this E over H, and the fiber of the L2 bundle EX, these are just L2 vector fields along M, and this L2 bundle itself is still a C1 manifold. Also, the tangent bundle is only C0. So this is, as a manifold, this is still a C1 manifold. Right. And then we have, so the gradient flow equation we can interpret as a C1 section. So we have C1 section. Let's call this sigma. And so if we have x point in H, so sigma of x is just dsx plus nabla fx. And then the zero set of this section, yeah, these are precisely the gradient flow lines. These are the gradient flow lines. Lines from x minus to x plus. And now we can use this, this section to explain globally what the linearization of the gradient flow equation is. So namely, we have the so-called vertical differential. First, we have the usual differential, dsx. So this, if we differentiate this section, we get a linear map from T sigma x e. But so let's assume that we are looking at a gradient flow line. So then txe, sigma x is just txe, and then this we can decompose as dxh plus dx. And now we have this picture. So we have here E, we have H, we have the projection, and now at the 0 we have a canonical splitting. First into E of x, and we have here txh, and therefore we can look. So we can define the sigma x. This is from txh to ex, and this is, we compose this differential with the projection from the tangent space of E to Ex, the projection along this txh. E sigma x, namely where Px is just projection along txh. And this vertical differential, this is what we call the linearization of gradient flow equation. This is the so-called linearization of gradient flow equation. And this is this Fredholm operator. And yeah, so you see that this and this d sigma x, this is then, this makes sense because we have here C1 manifolds. Okay, and yeah, when one goes back to the construction of how these Hilbert manifolds are constructed, they are usually constructed with the help of exponential map. And now the question which arises with your is, when now in Flur homology we have two-level manifolds. And then, when we have two-level manifolds, do we still have that this space of path is a Hilbert manifold? So, the question is if we have x1, x2, let's say a C2 two-level manifold, modeled on a scale of Hilbert spaces. This H2 compactly intense in H1, and we have 2 points, x1, x minus x plus in x2 is a space of path from x minus to x plus a C1 Hilbert manifold. Yeah, because if this is not C1 Hilbert manifold, then yeah, and then we cannot really talk about the linearization of the gradient flow equation, and then we cannot really make sense of the question, is it a Fredholm operator? As long as we don't know what the linearization is, we cannot ask, is it a Fredholm? Yeah, actually path in x2. Mm. And in general, we are not so sure if on a two-level manifold. So what we don't have on a two-level manifold, exponential map is not such a good idea on a two-level manifold, because now we have two different topologies. And so when we discussed this question, we came up with an additional condition which we think such a two-level manifold should have in order that we can reasonably address this kind of questions. And I would like to discuss this additional condition, and this is what we call tameness. A condition tameness. So let us assume that U in H1 is open subset, and we have f from U to H1 C2 function such that if we restrict f to, we can we have always this situation. So H2 is densely compactly included in H1, so we can restrict f to U intersected H2, and then we get a map from U times H2, and we want that this goes to H2 and is also C2. So this we definitely need to talk about two-level manifolds, but now we need some additional condition on these maps, and let me give the definition. F is called tame if for all points x in on level 2, but on U intersected at H2, there exists Wx in U, an open neighborhood of x, but open now with respect to H1. H1 topology. So we have H1 open neighborhood of x and some constant kappa bigger 0 such that for every other point U in this Wx intersected with H2 and for all vectors psi eta in H2. If we look at the second derivative of f at this point y and apply it to psi and eta and look at the 2 norm, we can estimate this by kappa, then the 2 norm of psi, the 1 norm of eta, plus the 1 norm of psi, 2 norm of eta, plus the 2 norm of y, the 1 norm of psi, the 1 norm of eta. That's what we call tame, and at the moment we are rather convinced that this is kind of an important condition we need. So what did we figure out about this notion? So the first thing we know, we proved is that composition of tame maps is tame. The proposition, composition of tame maps is tame. And thanks to this proposition, the notion of a tame two-level manifold makes sense, because now we can just ask that that transition maps in our two-level manifolds are always tame. And yeah, okay, atlas one can always define, but then what one would like to have is that one has compatibility of atlases. So if you have two tame atlases, then they are compatible if their union is again a tame atlas. And this compatibility should be an equivalence relation. Symmetry and reflexivity is clear, but transitivity is not obvious, and transitivity needs that this composition is tame. But from this we have the notion of tame two-level manifold. Makes sense. And then one can work out an example. So an example is if you have finite dimensional manifold, and if one looks at W22 loop space in W12 loop space, this is actually tame. So M is a finite dimensional manifold, and we have W22 loop space. This is contained in the W12 loop space, and this is a tame two-level manifold. And this uses, it's the following formula, which you all know. So if you look at the second derivative of f and g, then this is f prime prime g plus f g prime prime plus 2 f prime g prime. But what you see, that's thanks to Leibniz, but you see we have never f prime prime and g prime prime. So that's basically from this formula helps us to show tameness in this situation. So this, and then the theorem we proved so suppose that we have H1, H1, tame. And then let us look at capital phi. And this capital phi, this goes, so we are looking at the W12 space. We are looking at W12 maps from R to the top level, H1, and intersect this with L2 on the lower level. And so what we are, and we look at the map from this Hilbert space into itself, namely Xi is mapped just to decompose Xi with phi, and this is C1. And this, to show this, we need, I don't see without tameness how to get such a thing. Maybe that's one, and then I don't write 2, but I write 1 plus, because 1 plus contains 1, but is a bit better, because as I said before, for the linearization of gradient flow equation, we don't need just the manifold of paths, we also need the L2 bundle to be C1, and this we also have. So if we have T of phi, this goes from this space above times L2, but now the L2 bundle is not on level 2, but is on level 1. Xi, now we have Xi and eta, Xi here and eta here. The map is still from this space to this space. Is on Xi we just do what we did above, phi times Xi, and on to eta we apply the differential of phi Xi. This is also C1. And and so this already gives some special case that our chart transitions are C1 chart transitions. That's in the special case where we look at the space of path just from one point to one point, but two charts around this point. So we take x equals x minus equals x plus in x2, and we have two charts around x. So we have here, this is our infinite dimensional space x, and we have our little x, and we have our chart V1, maybe green chart. And we have our purple chart, V2, and we have two images. So we have here U1 in H1, and we have here image U2 in H2, and let's call this charts psi1 and psi2. And then we have here intersection. So we have here the intersection psi1 of V1 intersected V2. We have here the intersection psi2 V1 intersected V2. Let's call this U12, and let's call this U21. And if we have U, let's abbreviate U12, the xi's in W12 are H1 intersected L2 are H2, such that psi of S is in U1, respectively U2 for all S in R, and let's also abbreviate U12, where we require that psi of S is in U12 to 1. Then we have here transition map phi. Phi from psi1 inverse, psi2, U12 from this U1 calligraphic U12 to U21. This is then a tame isomorphism. And we have, and therefore the corresponding capital phi from U12, sorry, this was on the not calligraphic, and this here is the calligraphic, this is then C1 diffeomorphism. Psi 2. So this is a special case where we just look at the space of path from one point to itself. Now, if we look for channel path, then what we need is a parametrized version of this theorem. And this so for channel path, we need a parametrized version of the theorem. And actually in this parametrized version, this was not so straightforward. Because so far this compact, so we have in H2 in H1 we have this compact dense inclusion. So we could ask, do we really need compactness? We could also relax it just to dense inclusion, and up to here dense inclusion would be okay, but for the parametrized version it really became crucial that this H2 was compactly contained in H1. So this so we get C1 Hilbert manifold, and this uses crucially that H2 in H1, that this inclusion is compact. That was kind of surprising, but it was, we don't see how to get this parameterized version without this compact inclusion. Right. Good. Okay, so we have nice Hilbert manifolds, and what we are currently working on, so we have some notion of Flur function, and so what some general notion of Flur function which should contain this functions we get from Hamiltonian delay equations, and then we are that this general Fredholm theorem for gradient flow lines of Flur functions. That's where, so, and I think I stop here.